Now coming to next problem. The excess Gibbs energy of a binary liquid mixer at temperature and pressure is given by the expression G by RT is equals to minus 2.6 x1 minus 1.8 x2 multiplied with x1 and x2. G by RT in terms of x1, x2. First bit, find the expression for ln gamma 1 and ln gamma 2 at constant temperature and pressure. Second bit, show the expression satisfy Gibbs-Duhem equation. And third bit is d ln gamma 1 by dx1 at x1 is equals to 1 is equals to minus d of ln gamma 2 by dx1 at x1 is equals to 0 is equals to 0. This is the problem. The excess Gibbs energy of a binary liquid mixer at temperature and pressure is given by G by RT is equals to minus 2.6 x1 minus 1.8 x2 x1 x2. Find the expression for ln gamma 1 and ln gamma 2 at constant temperature and pressure. Second bit, show the expression satisfy Gibbs-Duhem equation. And third bit, d of ln gamma 1 divided by dx1 at x1 is equals to 1 is equals to minus d of ln gamma 2 divided by dx1 at x1 is equals to 0 is equals to 0. Now coming to solution. Here given expression g by rt is converted into x1 terms. So replace x2 with 1 minus x1 and simplify g by rt expression. Then we will get 0.8 x1 cube plus x1 square minus 1.8 x1. Then differentiate g by rt with respect to x1. This is also like partial properties problem. That is m1 bar is equals to m plus x2 d m by dx1 type problem. d of g by rt by dx1 is equals to 2.4 x1 square plus 2x1 minus 1.8. Then ln gamma 1 is equals to g by rt. This is proved in fugacity. ln gamma 1 is equals to g bar by rt. Therefore, this is in the form of partial property. That is equals to g by rt plus x2 d of g by rt by dx1. That is equals to 0.8 x1 cube plus x1 square minus 1.x1 plus x2 is replaced with 1 minus x1. That is 1 minus x1 into 2.4 x1 square plus 2x1 minus 1.8. Then simplify the expression. We will get the expression in terms of x1. That is equals to minus 1.8 x1 cube plus 1.4 x1 square plus 2x1 minus 1.8. Then calculate the ln gamma 2. That is equals to partial property of species 2. That is equals to g bar by rt is equals to g by rt minus x1 d of g by rt dx1. That is in the form of m2 bar is equals to m minus x1 dm by dx1. Then substitute the values of g by rt and d of g by rt. Then simplify. We will get minus 1.6 x1 cube minus x1 square. Now coming to next bit. Sigma xi dmi is equals to 0. This is the Gibbs-Duhem equation. In place of m, we have to substitute with ln gamma 1 and ln gamma 2 and open the sigma term. x1 d of ln gamma 1 plus x2 d of ln gamma 2 is equals to 0. We noted it 1. Equation 1. d of ln gamma 1 is equals to minus 4.x1 square plus 2.58 x1 plus 2. Now differentiate ln gamma 1, that is equals to minus 4.8 x1 square plus 2.58 dx1 plus 2.58 x1 plus 2. Rotate with equation 2. Then differentiate ln gamma 2 with respect to x1. That is minus 4.8 x1 square minus 2x1. And notate with equation 3. Now substitute equations 2 and 3 in equation 1. That means substitute the values of d of ln gamma 1 and d of ln gamma 2 in equation 1. Then simplify. We will get the answer is 0. That is the second bit. Now coming to third bit. We have to prove d of ln gamma 1 by dx1 is at x1 is equals to 1. That is equals to, already calculate ln gamma 1 with respect to x1. That is minus 1.6 x1 cube plus 1.4 x1 square plus 2x1 minus 1.8. We have to substitute x1 with 1. Then simplify, we will get 2. After that, we have to calculate minus d of ln gamma 2 by dx1 at x1 is equals to 0 is equals to 0. We know the d of ln gamma 2 by dx1 already in second bit. That is equals to minus 1.6 x1 cube minus x1 square at x1 is equals to 0. Now substitute x1 with 0. Therefore, answer is 0. It is proved. Bit 3 proved. D of ln gamma 1 by dx1 at x1 is equals to minus d of ln gamma 2 by dx1 at x1 is equals to 0. In this problem, given the relation of g by rt, then replace x2 with x1, that is 1 minus x1. Then all the expression in terms of x1. We know that ln gamma 1 is equals to g by rt. ln gamma 1 is equals to g bar by rt. Then calculate the partial properties of species 1 and species 2 in bit 1. Then satisfy the Gibbs-Hume equation, that is sigma xi dmi bar is equals to 0. So substitute in terms of n with g bar by rt. And in third bit, prove that d of ln gamma 1 by dx1 at x1 is equals to 1 is equals to minus d of ln gamma 2 by dx1 at x1 is equals to 0. We proved that is equals to 0. Now coming to next block. The enthalpy of a binary liquid system of species 1 and 2 at fixed temperature and pressure is represented by the equation H is equals to 400x1 plus 600x2 plus x1x2 multiplied with 40x1 plus 20x2. This is the given expression for enthalpy in joules per mole. Determine the expressions for H1 bar and H2 bar as functions of x1. Numerical values for the pure species enthalpies H1 and H2 and numerical values for the partial enthalpies at infinite dilution H1 bar and H2 bar. I repeat, the enthalpy of binary liquid system of species 1 and 2 at fixed temperature and pressure is represented by the equation H is equals to 400x1 plus 600x2 plus x1x2 multiplied with 40x1 plus 20x2. Here H is in joule per mole. Determine the expressions for H1 bar and H2 bar as functions of x1. Numerical values for the pure species enthalpies H1 and H2 and numerical values for partial enthalpies at infinite dilution H1 bar and H2 bar infinity. H1 bar infinity and H2 bar infinity. This is the problem. Here we have to calculate partial molar properties and numerical values of pure species enthalpies and numerical values for the partial enthalpy at infinite dilutions. Here we know the formulas for partial properties. That is, in binary mixer we have to calculate the partial properties of species 1 and 2. That is, m1 bar is equals to m plus x2 dm by dx1 and M2 bar is equals to M minus x1 dm by dx1. Here substitute M with H because given expression in terms of H, that is enthalpy. In the given expression, we have to replace x2 with 1 minus x1. Then simplify the H expression. We will get H is equals to minus 20x1 cube minus 180x1 plus 600. Then calculate the dH by dx. Differentiate H expression with respect to x1, that is equals to minus 60x1 square minus 180. Therefore, substitute dH by dx1 in h1 bar. We know the value of h and dH by dx. Then calculate the h1 bar. That is equals to 40x1 cube minus 60x1 square plus 120. After calculating h1 bar, calculate h2 bar by using h minus x1 dH by dx1. Here h1 bar is equals to 40x1 cube plus 600 at pure species. Substitute in H expression. Now second bit is calculation of pure species enthalpy. After calculating partial properties H1 bar and H2 bar, we have to calculate the pure species enthalpies. That means H1 and H2. Here we have to substitute x1 is equals to 0 for getting the value of pure species enthalpy of species 1 and x1 is equals to 1 for getting the value of pure species enthalpies of species 2. After substituting x1 is equals to 0 and x1 is equals to 1, we will get x1 is equals to 400 joule per mole and h2 is equals to 600 joule per mole. This is the second part. And coming to third part, calculation of partial molar properties at infinite dilutions. We already calculated H1 bar and H2 bar. For infinite dilutions, we have to substitute x1 is equals to 0 for H1 bar and x2 is equals to 0 for getting the value of H2 bar. After substituting x1 is equals to 0 for H1 bar is equals to 420 joule per mole. Similarly, we have to calculate H2 bar infinity by substituting x1 is equals to 1. Therefore, H2 bar infinity is equals to 640 joule per mole. In this problem, initially we have to calculate partial molar enthalpy of species 1 and partial molar enthalpy of species 2. After calculating partial molar enthalpies, then calculate the numerical values per pure species. Then substitute x1 is equals to 1 and x2 is equals to 1 in enthalpy expression. After that, we have to calculate the H1 bar infinity and H2 bar infinity at infinite dilutions and calculate the H1 bar and H2 bar at infinite dilutions. H1 bar infinity is calculated by using x1 is equals to 0 and H2 bar infinity calculated from x1 is equals to 1, that is equals to 640 joule per mole. Now coming to next topic, ideal gas mixer. Now coming to ideal gas mixer. Now coming to next topic, ideal gas mixer. If n moles of an ideal gas mixer occupy a total volume Vt at temperature T and pressure P is expressed as P is equals to nRT by Vt. Denote with equation 1. If Ni moles of species in this mixer occupy the same total volume alone at the same temperature and pressure, Pi is equals to Ni by RT. If n moles of an ideal gas mixer occupy a total volume Vt at temperature T and pressure P is equals to nRT by Vt. That is PVT is equals to nRT. This is the ideal gas equation. Then taking the term Vt to right hand side of the equation. Therefore, P is equals to nRT by Vt. Denote with the expression 1. Denote with equation 1. Similarly, if Ni moles of species I in this gas mixer occupy the same total volume alone at the same temperature and pressure is Pi is equals to NiRT by Vt. That is denoted with equation 2. Now divide equation 2 with 1. Therefore, Pi by P is equals to Ni by N is equals to Xi. We denote this equation with 3. Here, Xi is the mole fraction of species I in the ideal gas mixer. Pi is the partial pressure of species I. Actually, an ideal gas is a modal gas. Actually, an ideal gas is a modal gas comprised of imaginary molecules of zero volume that do not interact with other molecules. Each chemical species in an ideal gas mixer has its own private properties, uninfluenced by the presence of other species. This is the basis for the statement of Gibbs theorem. Gibbs theorem is defined as partial molar property of species I in an ideal gas mixer at a given temperature and pressure is equal to its pure property at same temperature, but the pressure is equal to partial pressure. But the pressure is equal to partial pressure. Mathematically, it is expressed as mi bar Ic at t comma p is equals to mi Ic at t comma pi. We noted this equation with 3. Now coming to partial molar enthalpy. Hi bar Ic at t comma p is equals to Hi Ic t comma pi. For ideal gas enthalpy, it is a function of temperature and independent of pressure. For ideal gas enthalpy is dependent on temperature but independent on pressure. So Hi bar Ic at t comma p is equals to Hi Ic at t comma pi. This is coming from Gibbs theorem. Noted this equation with equation 4. Here, partial molar enthalpy of species I in an ideal gas mixer at given temperature and pressure is equal to its pure enthalpy at same temperature and pressure Pi. Here, partial molar enthalpy of species I in an ideal gas mixer at given temperature and pressure equal to its pure enthalpy at same temperature and pressure. Now coming to partial molar entropy. From the definition of entropy, ds is equals to dq by t. From first law of thermodynamics, dq is equals to du minus dw. Then substitute in place of q with du minus dw. Here, from the definition of enthalpy, H is equals to U plus P. Then U is equals to H minus P. Substitute in place of U with H minus P. d of H minus PV minus dW by d. Then simplify, we will get ds is equals to dH minus VdP by d. From constant pressure, dH is equals to Cp dt. For constant pressure process, enthalpy is equals to integral Cp dt. dH is equals to Cp dt. And from ideal gas law, V is equals to RT by P. Then substitute those terms in ds expression. That is, ds is equals to Cp by d dt minus RT by P dP by t. Here, Tt gets cancelled. Therefore, ds is equals to Cp by t dt minus R by P dP. For constant temperature, ds is equals to minus R by P dP. In ds is equals Tp by T dt minus R by P dP expression, dt term gets cancelled at constant temperature. Therefore, ds is equals to minus R by P dP. For an ideal gas, dsIg is equals to minus R by P dP. Then integrate between the limits Pi to P. After integration, we will get SiIg at T comma P minus SiIg T comma Pi is equals to minus R ln P by Pi. Integration of 1 by P is ln P. Then substitute the limits. Then we will get SiIg at T comma P minus SiIg T comma Pi is equals to minus R ln P by Pi. We know that for ideal gas, Pi is equals to Xi into P. Then substitute with Xip in place of Pi. Therefore, SiIg at T comma P minus SiIg T comma Pi is equals to minus R ln P dash by Xi minus R ln P by Xi P. Pp gets cancelled. Therefore, SiIg T comma P minus SiIg T comma Pi is equals to minus R ln 1 by Xi. Taking the minus term into ln term, that is minus of 1 by Xi is equals to Xi. Therefore, SiIg T comma P minus R ln Xi is equals to SiIg at T comma Pi. Taking the term R ln Xi to right hand side. Therefore, SiIg T comma Pi is equals to SiIg T comma P. Therefore, Si bar Ig at T comma P is equals to SiIg at T comma Pi. This is from Gibbs theorem. Therefore, Si bar Ig T comma P is equals to SiIg T comma P minus R ln Xi. From Gibbs theorem, Si bar Ig T comma P is equals to SiIg at T comma Pi. Then substitute this one in Si bar Ig at T comma Pi is equals to SiIg T comma P minus R ln Xi. Therefore, Si bar Ig at T comma P is equals to SiIg at T comma P minus R ln Xi. Therefore, Si bar Ig is equals to SiIg minus R ln Xi. Now coming to partial molar properties, that is partial molar Gibbs free energy. We know the definition of Gibbs energy. G is equals to H minus Ts. For ideal gas, Gi bar Ig is equals to Hi bar Ig minus T into Si bar Ig. From partial molar entropy, Gi bar Ig is equals to Hi bar Ig minus T into SiIg minus R ln Xi. From partial molar entropy, Gi bar Ig is equals to Hi bar Ig minus T into SiIg minus R ln Xi. From partial molar enthalpy, Gi bar Ig is equals to Hi bar Ig minus Ts Ig plus Rt ln Xi. Therefore, substitute in place of Hi. Gi bar Ig is equals to Gi Ig plus Rt ln Xi. Therefore, replace with H minus Ts is with G. That is from the definition of Gibbs energy. Now coming to partial properties of ideal gas mixture. We know the summability relation, that is M is equals to sigma xi mi bar. For an ideal gas, Mig is equals to sigma xi Mig bar. Here replace the term M with enthalpy. That is Hij is equals to sigma xi Hi bar Ig. Therefore, Hij is equals to sigma xi Hij. This is from Gibbs theorem. Hi bar Ig is equals to Hij. Then substitute M with entropy, that is S. Therefore, Sig is equal to sigma Si bar Ig. Previously, we derived the expression for Si bar Ig is equals to Sig minus R ln Xi. Then replace in place of Si bar Ig. Therefore, Sig is equal to sigma Xi into Sig minus R ln Xi. Therefore, Sig is equal to sigma Sig minus R sigma Xi ln Xi. Then substitute M with Gibbs energy. That is Gi is equals to sigma Xi Gi bar Ig. Previously we derived Gi bar Ig is equals to Gi Ig plus Rt ln Xi. Then substitute in place of Gi bar Ig. Therefore, Gi is equals to sigma Xi Gi Ig plus Rt sigma Xi ln Xi. This is about ideal gas mixture.